exponential growth and decay stuff that you did in pre-calculus, maybe written a little differently. Remember that half-life is the amount of time needed for a substance to decay to half of its original amount. You can always solve for the half-life if you're given it, right? Like the half-life of carbon-14 is like 5,730 years, and so you can plug that in. It's pretty close, right?
I don't know.
I think it's
surprised you just
Is that true?
I think so. I said the next one. I
didn't know it, so.
I know it really because the first year I taught out of this book, we did this, and then in AP Bio, the AP Bio book said the half-life of carbon-14 was a different year, and the Ziegler boys were like, in calculus it says half-life was 5,730 years. One of these books is wrong, and we discovered that the biology book was wrong, and the calculus book was right. But it seems like that sometimes they say approximately, like sometimes they say the approximate half-life is just 5,700 years, like they leave off the 30. I don't know. It's very weird. But I believe we go with the 5,730 years is the half-life of carbon-14, which is what they use to like say how old things are when they find them, right? Like this rock is whatever years old. I don't know. Anyway, you can always work it out. Like you can say like if you have y equals c e to the kt, and if you know the half-life, then you could say half of c would be left after 5,730 years, and you could always solve for k just doing the math. Does that make sense? Like that's how we've done it before, because you can just cross the c's out, then you can ln, and you get ln of 1/2 equals 5,730k. And then if I divide by, what am I trying to solve for here? No, I'm sorry. Well, if I match this up, I'm solving for the half-life, right? So I would divide by k here. Oh, look, mine's different than this. Yes. Because half-life means how long it takes for half of it to be left. Does that make sense? The one on your homework from the other day, there was one that talked about doubling, like the time it took for an amount to double in an account. Find how long it takes to triple in the account, right? If they don't tell you how much it starts with, and they tell you how much is left, you can always set that up here. So like I said, if the original amount is C, right, that's my original amount, and after 5,730 years, half of it is left. So if C is the original amount, does it make sense why I put half of C there? And like the one that was 40, I think it was 49, so I helped to come up with it. It said like it takes 7 years for the amount to double, but they didn't tell you how much you started with. That's okay, because if you know your original amount is A, and it took 7 years to double, then that means what's left after 7 years is 2A. Or the amount to triple, you can put 3A. And so you don't have to actually know how much you start with if you know what amount is left, half or double or triple. Does that make sense? Oh yeah, you can totally make them up, right? Because if it's going to double, you can say I started with 1, so what's left is 2, right? That's the same thing. I just always use letters because I'm a math person, and I like to just say, well, the A's just cancel out. But you could say 100, and then you have 200 left. Either way, if you're doubling it, you're always going to be left with 2 over here. If you have half of it left, you're always going to be left with half of it. So it doesn't matter as long as you do the ratio right. Does that make sense?
So like whatever.
Mm-hmm.
So like, is it okay if we use C instead of like A70?
Yeah.
Like it doesn't matter.
Right. Okay, so I just wanted to point out that this works. If you know the half-life, it'll be equal to ln of 2 divided by k. But when I solved it out, I got that if I solved it to match this, I would get ln of 1/2 divided by k. Do you see the difference between that? Here's why, all right? The book is just assuming that k is greater than 0. When you plug it into the half-life formula, you have to put a negative, because if it's getting smaller, like, you have to put the negative up there. So I just wanted you to be aware that if you use this formula, when you plug it back into your formula, like, you have to put the negative in front of it, or you're not going to get that it's getting smaller over time. You're going to get that it's getting bigger. I tend to forget this. I don't know why. It's easy formula. I tend to forget it, and I just do the work every time. Like, it's not that much work to plug it in and solve it if you're solving for k. But this is a really nice formula if you remember. after 10,000 years is 2 grams. Find the initial quantity and the amount after 1,000 years. Ready, go. What do we start with? What's my equation that I'm talking about if I'm talking about something growing or decaying?
But like 5,730
To find that half, or to find K, we could do that. But what's my equation that I'm going to try to write to talk about exponential growth and decay? Like, what's our go-to equation? So, you have to make a decision here on how you want to do these problems. If you want to use the formula I just gave you, where the half-life will equal ln of 2 divided by k, you have to know that this is getting smaller over time, right? If it's getting smaller over time, that means that k has to be a negative. Does that make sense to you? If you think you're not going to remember whether to make k negative or positive, then you just need to plug in the information and solve for k that way. Because that will always give you a negative k if you plug in the information. So this is what I do, because I forget that formula. I say, oh, if the half-life is 5,730 years, then I can say half of c is left after 5,730 years. Right, if I forgot the formula that I just gave you. And I can say ln of 1/2 equals 5,730k, or that k equals ln of 1/2 divided by 5,730. And that will give me a negative value for k, so I don't have to think about should I put a negative in there. If you do what I just gave you on the other page, half-life equals ln of 2 divided by k, if you're solving for k, you would say 5,730 equals ln of 2 divided by k, or k times 5,730 equals ln of 2, or k equals ln of 2 divided by 5,730. The difference between these two is that you have to know to put a negative up there if you use this formula. Does that make sense of what I'm saying here? Yeah, maybe we should just add a negative to our half-life equation, right? Well, the reason they don't is because they throw in the reasoning where k is greater than 0, right? But you're right. Like, why don't we just say, or we could change this to ln of 1/2 if we wanted to, right? That would be the same thing. Yeah. So you could just put a negative here. That would work that out so you don't have to remember that. I don't know. I just wanted to make sure I point that out because if you look in the book, they don't put the negative in front of it. But
Why don't we say
right, which is negative ln of 2. I agree. I think it's because they want you to realize if it's exponential decay, then you put the negative, like then k is negative. But I don't know. I tend to just do this. But yeah.
Just coincidence that K is the ln of 3
No, that will, if it's a half-life, that will always work like that. Yes. Which is why they give you that formula on the page before here. It always works like that. I just always forget the formula. And it's just as quick for me to solve it. So, I don't know. Again, if they ask you to tell you what is K, I think this, or however you want to write this, is like that's the exact answer. If you're going to type this in your calculator as a decimal when you're working out other stuff, remember to use a lot of decimals. AP rules are around to 3 decimals, but that means like final answers round to 3 decimals. So if you type this in your calculator, either way you type it, ln of 1/2, negative ln of 2, it's the same thing. You get like negative, it's really, really small, right? 0.000120968. Did you get that? I tend to type the fraction in, but I'm okay with lots of parentheses in my calculator. If you feel like you struggle with parentheses, just type out the whole decimal. Should be good enough to 3 decimal places when you go from there. You have to have k before you can do anything else. So they tell us that the amount after 10,000 years is 2 grams, right? That means they're giving us a t value, and they're giving us the ending amount. We just solve for k, which means we should be back. We should be able to go back and solve for C now, right? So if I have y equals CE, I'm just going to write to the kt power here, where k equals this big giant number. So I don't have to write that big giant number up there. That's a nice thing you can do on the AP exam. If you say k equals this big giant number, and then in the problem, you can just leave the letter, so you don't have to write all those things. You got to know where to plug stuff in, right? Like, this is not calculus that we're doing right now. This is just pre-calculus. Really, algebra 2, we did stuff like this, where I can say my ending amount is 10,000. I don't know what I started with. Nope, just kidding. That's not my ending amount. Right, that's my time, sorry. My ending amount is 2 grams, and that was after 10,000 years. And again, I'm just going to put K up there, and I'm going to type that whole thing in there for K when I do it on my calculator. And you see how we can solve that for C? No derivatives, no integrals, just solving that problem. So I'm really just going to take 2 divided by this. So on my calculator, I'm going to take 2 divided by e to the 10,000 times, and then you can type this in if you wanted, or you can type that decimal in. 0.968. And I got C to equal 6.705 if I was rounding to 3 decimals. And so then if you find C, then you can do anything that they ask you. And so then they ask you another question. So find the initial quantity. We did that. This K value, that's called like our constant of proportionality. Like that's the math term of it. Really, it's the rate of decay. Like it's what rate it's getting smaller at. But find the amount after 1,000 years, this just becomes a total calculator problem now. If the original amount is 6.705, e to the k times 1,000, like I don't even have to divide anything, right? I just type that directly in my calculator. It's decaying, which means my answer should be getting smaller, right? .941, that's what I got. Did you get that? You got to know what equation to start with. You got to be able to find K, whether it's just doing the math to find K or using the formula to find K, and then you got to know where to plug the stuff in to go from there. Let's look at that. Ooh, I like this. Maybe, okay, maybe this one's not as exciting as number 4, but that's okay. A certain bacteria increases continuously at a rate proportional to the number present. If there are 100 present at a certain time and 300 present 5 hours later, how many will there be 10 hours after the initial time? And then how long does it take to double the number of bacteria? This is why they don't tell you to put the negative on that half-life formula. Because they want you to read the problem and to think about whether it's growth or decay. If it's growth, K's positive. If it's decay, like half-life stuff, then K's negative. And so that's why they don't put it in there. We can adjust that formula that I gave you for the half-life, because you're right, it will always be negative if it's half-life. But that's why they don't give that to you in the book, because they want you to read this and say, oh, bacteria is increasing, so when I write this equation, I know that my K is positive. Where if it's a half-life, I know that I could just put a negative in front of that and then use that formula. But as long as you do it correctly, I don't care which way you do it. If there are 100 present at a certain time and 300 present 5 hours later, is that enough information for me to plug everything in to solve for my K? That's where you have to start every time. If it's a half-life, then you can just use the formula for half-life. But if it's not half-life, you have to solve for that constant of proportionality, that growth factor or decay factor. And so they have to give you enough information. The big issue is making sure you plug things in correctly. If there was 100 present, and then 300 present 5 hours later, what goes here, the 100 or the 300? There's 300, because there's 300 after there's 100 present 5 hours later, right? And if I divide by 100, I'm just going to get 3 here. And this is a whole lot of ln stuff in these problems because these have e in them. We should be pretty advanced in this class in that you don't have to show me every step of work. Like I pretty much do this in my head from here, and I say ln of 3, that's going to cancel the e out. And if I divide by 5, that would give me k. Right? And I'm okay with that. I'm also okay if you want to show more work than that. And if you know k, then you can find all this stuff, right? Like how many, will there be 10 hours after that initial time? Right? They never really say 100 is the initial amount, but they say after the initial time they gave us earlier. And so we have this lovely equation, y equals 100 e to the kt. This one's not such a bad k. I'm going to write that as ln of 3 divided by 5 t. And if I wanted to find this, do you agree I could just plug 10 in here? If I wanted to find how long does it take to double the bacteria, that means I'm looking for t, so what would I have to put over here for y? 200, and solve it from there, right? I'm not going to work all this out because we're running short on time and I want to get to the better ones. But this is just doing the math. So after 10 hours, you could just do that. Over how long does it take to double, we would just say 200 equals 100 e to the ln of 3 divided by 5 t. Right? Look for what you're trying to find. How long? I'm trying to find t, so you should be able to plug everything else in. And then you can work that out. Let's look at this. See, look, this is why I'm annoyed, because look at this problem. I took this problem from the book. After the same problem that said carbon-14 was 5,730 years, they said scientists who use carbon-14 dating that use 5,700 years for its half-life. What? Like, why did they change it? Isn't science supposed to be exact? Anyway, on a test, I'll tell you the half-life. Like, I won't expect that you just memorize the half-life of carbon-14. So I'll tell you which one to use, so that way that we would all be using the same numbers. But we're going to use 5,700 on this, or we can use 5,730 if we want. I don't care. It says find the age of a sample in which 10% of the radioactive nuclei originally present have decayed. So it says that means 90% is left. Do you agree with that statement? So instead of talking about doubling or how long is it going to be for this much to be left, they're making you look for like a percentage that's left, which is just kind of making you think a little bit more. So again, I have my equation, y equals CE, and this is where if you're, I don't know what to do, I'm just going to leave it as KT since we changed our formula. They use carbon-14 a lot, which is one that you can, I don't know, you can almost memorize the formula for the half-life on it. But again, you can solve for the half-life using the formula I gave you, or you can just plug it in and solve for K that way. If we want to change the formula that I gave you on the first page, right, we said we're going to change it to the half-life equals the negative ln of 2 divided by K. I don't know why they set it up like that, because we're always looking for K. Doesn't that mean that K will always equal the negative ln of 2 divided by the half-life? Yes? So we can say, if we're changing our half-life to 5,700 on here, K would equal negative ln of 2 divided by 5,700. Step 1, find your constant of proportionality, or your rate of decay. This one says, if 10% of the nuclei present have decayed, then you need to be able to realize that means that 90% is left. So again, I tend to use the letters here. If C is how much I started with, how could I show that 90% of what I started with is left? Right? Or if you wanted to make a number up, if you want to say I started with 1, then I would just be left with 0.9. Or if you wanted to say I started with 5, I would be left with 0.9 times 5, right? Whatever that initial amount is. I just always use C because I know that that's just gonna divide out every time. And then I have, I'm just gonna again write to the KC power. And then I'm just solving for time on this. But I just want to make sure we talked about one with the percentage on it. I got like 866 years, right? We have ln of 0.9 divided by k, which is negative ln of 2 divided by 5700, or you can type that decimal in there. Might be 6730, I don't know. Syntax error, that's what it is. Okay. 866.418 or 417 if you truncate there. So make sure you read those. There's some good questions on your homework about that. What time do we have here? 2 soon. 2 soon. Okay. This is the one I should have skipped number 2 and then there's no mistake. A colony of bacteria is grown under ideal conditions in a laboratory so that the population increases exponentially with time. At the end of 2 hours, there are 5,400 bacteria. At the end of 4 hours, there are 48,600 bacteria. How many bacteria were present initially?
For the first 2 hours and use the 2 hours as the start.
I don't know.
This doesn't really matter. I mean, everything that's anywhere you want to start. I'm gonna just,
But how many bacteria were present initially? So then what would you do to go backwards?
well, you could find the right, could you just go backwards from the 2 hours?
I don't know. I'll have to work it out.
Maybe solve for C on workbooks and like plug it in for the other.
Yeah, I kind of let's see here. I said for the first one at the end of 2. How about this? You try what you want to try, and you try what you want to try, and we'll start with this tomorrow. Try your homework. There's one like number 4, but the rest of them you should be able to do. But try them. I think yours are going to be able to look like this too. All right, it's a good one.
I just want to say the office, please. I need
Did I
Anthony
put the homework on
Hendrickson,
here?
Colt Giverson, Cheyenne Burton, Jessica Gibson, Dakota Williams,
Actually, it's all
The Office, please.